Welcome back. So we would like to factor this. Same method we did in the last video. So we're going to try synthetic division. 4, -7, 2, 9, -6, and -2. Now, we're trying to guess a number here so that we get 0 here. And we learned about the rational roots theorem, which said if there are rational roots for this polynomial function f, then they must be in a certain format. So there was this number p, which we said, if we look at the constant term, p can be any integer that goes into that. So plus or minus 1 and plus or minus 2 are the integers that go into -2. And then there was this number q, where we said, those are all the integers that go into the leading coefficient. So that would be plus or minus 1, plus or minus 2, and plus or minus 4. And then we said the rational roots that are possible are of the format some number in here divided by some number in here. So we take the combinations, 1 over 1, 1 over 2, 1 over 4, and then 2 over 1, and then 2 over 2 is already 1, and 2 over 4 is already 1/2, so this is the list. So if we have rational roots, then they can only be these possibilities. So we start checking, right? So let's start with 1. It's going to be 4, 4, -3, -3, -1. And then -1, +8, 8, 2, and 2. Okay, off to a good start. So we already have one of the factors, x minus 1. And just for good measure, we should check to see if the same one happens again. It does not, right? Because those do not add up to 0. Okay, so we can stop here and say 1 is no longer a 0. So we'll try -1, see what happens. 4, then we have -7, +7, 6, -6, then we have 2, and we have -2. Okay, so we know that -1 is a 0. So we're going to say x plus 1 is another factor. So before we move on, we should try -1 one more time just to check. 4, then -4, -11, +11. Okay, so this is not going to work. So +1 and -1 are done. Then we go to 1/2. So let's try 1/2. So then we go to 4, and then we go to here. This is going to be -5, and then -5/2. Once we get out of the integer territory, we can give up. So now we try -1/2. -2, -9, and then we have 9/2 here. Same problem. Once we're out of integer territory, we must give up. Okay, so positive and -1/2 are done. Then we'll try positive -1/4. So 1/4, then we have, this is going to be -6, then -6 times 1/4 is -3/2. We are out of integer territory, so we give up, okay? Then we'll go to -1/4. This is going to be -1, -8, multiplied by -1/4 is 2, 8, and -2. Okay, so we have x plus 1/4 now, okay? So we can then take a 4 out of this and say this is going to become 1, -2, and +2. Okay. But now here's the concern. So the front number now is 1, which means our valid options for q, we no longer have 2 and we no longer have 4, because neither of those numbers goes into 1, which means these are no longer options. So the only things left to try that are rational are plus or minus 2. And notice, you already know that we can use the quadratic formula to guarantee the answers from here, but I'm just going to try something, just to make a point. So I'm going to try the number 2. So I go 1, 2, that becomes 0, 0. That does not add up to 0, okay? So 2 is not a root of f. So then I try -2. 1, -2, -4. That does not add up to 0. So I'm out of rational options. These are both gone, and I need 2 more of these factors to get 5 factors total, because I have a degree 5 polynomial, but I've used up all my possible rational roots. So the conclusion here is I have two more roots, but they are not rational. So I have to use some other method to find them. Well, in this case, we already know we can use the quadratic formula. We can say, why don't we say x squared minus 2x plus 2, and we'll let this equal to 0. So we can use the quadratic formula. X equals 2 plus or minus the square root of 2 squared minus 4 times 1 times 2 all over 2 times 1. This is 2 plus or minus, that's 4 minus 8, which is negative 4. So the square root of negative 4 is 2i, all over 2. 1 plus or minus I. So I know, because these are the zeros of f, I know that the factors are x minus parentheses 1 plus I, which is going to be x minus 1 minus I, and the other one is going to be x subtract 1 minus I. So that means x minus 1 plus I, and these two are my factors. So I can fill it in up here. I'm going to have x minus 1 minus I and x minus 1 plus I. And then finally put the leading coefficient in front, and we have fully factored f of x. We have another theorem on the board, very ominous. And here we have another example. I have a polynomial that I'm trying to factor. And this time I'm given that this number, 2 plus I, which is not a real number, is a 0 of f of x. Now let's imagine we don't know what to do with this information at the start, so we just try to do this problem in the same way we did the last one. So we're going to do synthetic division, and we're going to try to guess a number in the box that will produce a 0 remainder. And let's start by referring to the rational roots theorem. So we say the rational roots can be, p represents any integer that can go into 25. So I can say plus or minus 1 plus or minus 5, or plus or minus 25 are the options. And then q represents any integer that can go into 1. So plus or minus 1 are the options there. Which means all of the possible rational roots p over q are going to be any number here divided by any number here, which is going to be plus or minus 1, plus or minus 5, plus or minus 25. Those are the only possible rational roots. So let's imagine we start to try them. Now, if you're bored, you can try all 6, just to confirm. But I'm going to save you some time. None of those 6 numbers works. So it turns out all of these are dead numbers to us, which means none of the zeros of f of x is rational. Because if it were rational, it would have to show up in this list. So now we're stuck. That's where this comes into play. This 2 plus I is a 0, which means if I put the 2 plus I here, I should get 0 right there. Let's see what happens. So the 1 comes straight down. 1 times 2 plus I is 2 plus I. When I add those together, the negative 2 and positive 2 cancel, and I just get I. Then I times 2 plus I, so I times 2 is 2I, and then I times I is negative 1. So this is what happens. When I add the 2 and the negative 1, I get 1, and then I get plus 2I. So now I'm supposed to take 1 plus 2I and multiply by what's up here. So if I do that real quick, 1 plus 2I multiplied by 2 plus I is going to get me 1 times 2 is 2, 1 times I is I, 2I times 2 is 4I, and 2I times I is negative 2. Negative 2 and positive 2 cancel, and I get 5I. So if I add those together, I get negative 10 plus 5I. And then I take this times what's up in the box. That's going to be negative 10 plus 5I multiplied by 2 plus I, which gets me negative 10 times 2, negative 10 times I, positive 5I times 2, and then 5I times I gets me negative 5. So these cancel each other, and I get negative 25. And lo and behold, I get 0, just like I was supposed to. Okay. But now, when we go on, here's the problem. I have now non-real coefficients in the quotient. And so I have to start guessing numbers in the box that are not rational, because none of those worked. I have to figure out something that is non-real, perhaps, that will work here. That's where this comes into play. So it says, if the original f of x is a polynomial with real coefficients, which we do have, all of our coefficients up here are real. Okay? If a plus bi, a complex number, is a 0 of f, then the complex conjugate a minus bi is also a 0 of f. So since we have 2 plus I is a 0, the complex conjugate 2 minus I is also a 0. So let's do synthetic division with 2 minus I. So I'll put the 1 here. 1 times 2 minus I is 2 minus I. These two add up to make 2. Then 2 times 2 minus I is 4 minus 2i. These add up to make 0. 1 plus 4 is 5. 5 times 2 minus I is 10 minus 5i. And this adds up to 0, as it should, because the complex roots theorem told us that this would be a 0. Now we're down to a quadratic. And once you get to a quadratic, you know you can use the quadratic formula to get the last two zeros. So I can say x is equal to negative b plus or minus the square root of b squared minus 4 times 1 times 5 all over 2 times 1. So this is going to be negative 2 plus or minus, that's 20 right there. So 4 minus 20 is negative 16. Square rooting that gives me 4i. So this is going to be negative 1 plus or minus 2i. So now I know my zeros are 2 plus I, 2 minus I, and then negative 1 plus 2i, negative 1 minus 2i. You see the complex conjugate showing up there as well. So I know that finally my f of x has to be x minus that, which is minus 2 minus I, then x minus that, which is minus 2 plus I, and then x minus each of those, so that's x plus 1 minus 2i, and x plus 1 plus 2i. And then the coefficient in front is just 1. So this becomes my factorization of f. Now let's imagine that you are absolutely appalled by the idea of putting non-real numbers here into synthetic division, and you just really never want to go through this process in your life. There is an alternative. So the deal is, we know that this is a 0, which means we know that this is a factor, right? We know that from the start. And using the complex roots theorem, we know that x equals 2 minus I is also a root, which means we know this is a factor, right? So we know these two are factors off the bat. So what if we were to take these two factors, which we know are factors of f, and multiply them together? So what if I took x minus 2 minus I multiplied by x minus 2 plus I? Well, I can distribute this in sort of the basic way. Or I can think of this as, isn't this x minus 2 minus I and x minus 2 plus I? So that's a difference of squares. This becomes x minus 2 squared minus I squared, which is just plus 1. So I can write this as x squared minus 4x plus 5, because that's going to give me a 4 plus 1 is 5. Okay, so evidently this is the same thing as those two put together. So what I could do is I could say, why don't I take my original polynomial f of x and divide by this using polynomial long division? Let's see what happens. So x squared goes into here, x squared times. So that times all of this gets me x to the 4th minus 4x cubed plus 5x squared. And I subtract everything. So this becomes 2x cubed minus 3x squared. Bring down the minus 10x. Then x squared goes into here, 2x times 2x cubed minus 8x squared plus 10x. Subtract everything gets me positive 5x squared minus 20x plus 25, and this goes into there 5 times. 5 times that is 5x squared minus 20x plus 25, and I get exactly no remainder, which is what should happen. Yeah? So what I have just discovered by doing that is f of x will factor down into that, which is the divisor, times the quotient, which is that. So really, I can rewrite this as x squared plus 4x, sorry, x squared minus 4x plus 5 from there. And then here is going to be x squared plus 2x plus 5, which is that. Okay, so now that I have this factorization, if I want to go back to here, so I already know where this came from. That came from those two factors. I can take this and use the quadratic formula to get the last two factors. So if you decide you never want to do this in your life, that's okay. All you have to do is take the factors you know from the two given zeros and then distribute so you get, with all real coefficients, the quadratic form of those two factors, and then you perform polynomial long division to get the quotient. And then you fill out the final steps by doing the quadratic formula. I don't know that this is any easier or shorter. Personally, I'm a big fan of this approach. And if you like this, it works. But some textbooks and some teachers insist on doing it this way. I just want you to know that both of those are viable. All right. Thanks for listening. Take care.